Look up at the night sky. You see stars, galaxies, and vast stretches of emptiness, an ocean of darkness that seems endless. But what if that darkness isn't as empty as it appears? What if, hidden within the void, there are forces at work so immense and mysterious that they challenge the very foundations of our understanding of the universe? For decades, we've believed that the cosmos is governed by the laws we can observe and measure. But what if we've been missing something colossal, something that operates on a scale so vast it defies imagination? Scientists have uncovered a phenomenon that raises exactly these questions, a cosmic mystery known as dark flow. Imagine the entire universe with its billions of galaxies, all moving in a specific direction as if being pulled by an invisible hand. Not because of gravity from something we can see, but because of something entirely unknown, something beyond the edges of our observable universe. This isn't science fiction. This is real. Galaxies are streaming toward a point in space we cannot explain, as if the universe itself is flowing toward a destination we have yet to discover. It's a finding so startling that it forces us to reconsider everything we thought we knew about the cosmos. In this video, we're going to explore 25 of the most fascinating mysteries surrounding dark flow, each one more puzzling than the last. From the possibility of other universes exerting their influence on our own, to the idea that our reality might be just one small part of a multiverse far grander than we ever imagined. We'll journey through the evidence, the theories, and the unanswered questions that make dark flow one of the greatest enigmas of modern cosmology. This is more than just a story about science. It's an invitation to wonder, to question, and to marvel at the profound mysteries that lie just beyond our reach. So settle in, open your mind, and prepare to explore the unknown. The discovery of this phenomenon began not with a grand revelation, but with a persistent, nagging inconsistency in the data. For years, scientists have used the cosmic microwave background, the faint afterglow of the Big Bang, as a stationary backdrop against which to measure cosmic motion. It's the ultimate fixed reference point, the oldest light in the universe. By studying the subtle temperature shifts in this radiation caused by the motion of galaxy clusters, a technique known as the kineticsunyaev-zeldovich effect, researchers can map how these colossal structures are moving through space. The expectation was always that these movements would be random and local, governed by the gravitational tug of war between visible mass. What they found, however, was anything but random. Instead of a chaotic jumble of motions, the data revealed a startlingly coherent flow. Hundreds and later thousands of galaxy clusters were all streaming in the same direction at astonishing velocities, some estimates reaching over 600 miles per second. To put that into perspective, that's a speed fast enough to travel from Earth to the Moon in roughly 10 minutes. This wasn't a gentle drift, it was a powerful, coordinated current cutting across the cosmos. And the most baffling part was the scale. This flow wasn't just affecting a few neighboring clusters, it was detected across billions of light years, a signature of motion on a scale so vast it should be impossible according to our standard model of cosmology. This model, known as the lambda cold dark matter model, is built on the principle that the universe is, on the largest scales, homogeneous and isotropic. That's a fancy way of saying it should look roughly the same in every direction, and that matter should be distributed fairly evenly. The force of gravity from this matter, both seen and unseen as dark matter, dictates the motion of galaxies. While local movements are expected, a bulk flow of this magnitude and coherence directly challenges this foundational idea. It suggests that there is something out there, far beyond the edge of what we can observe, exerting a gravitational influence so profound that it is pulling millions of galaxies toward it. This something is not on any of our maps. It is a gravitational anomaly of unimaginable proportions, a shadow in the cosmos whose presence we can only infer from the restless motion of everything we can see. And so we arrive at the heart of the mystery, a set of impossible coordinates etched into the fabric of the cosmos. When researchers traced the trajectory of this vast river of galaxies, all those millions of clusters streaming in unison, their paths did not lead to a known supercluster or a familiar gravitational anchor. Instead, their motion converged on a single, seemingly arbitrary point in the sky, located in the southern constellation of Centaurus. The coordinates are roughly right: ascension 10 hours, declination -20 degrees. To the unaided eye, this patch of sky looks no different from any other, a random scattering of stars. But according to the data, it is the epicenter of one of the greatest cosmic puzzles we have ever encountered. This focal point, what we might call the gravitational epicenter of the dark flow, presents a profound and immediate challenge. The standard model of cosmology depends on the universe being uniform on the largest scales. There should be no special direction, no preferred axis, and certainly no single point toward which everything is drawn. The existence of this coordinate shatters that principle of isotropy. It suggests that our observable universe, the sphere of space some 93 billion light-years across that we can see, is not the whole story. Something immense and unimaginably powerful lies beyond its horizon, and its gravitational pull is so dominant that it is literally steering the motion of galaxies within our own visible realm. Why Centaurus? That question haunts cosmologists. It's not a direction that aligns with any known large-scale structure, like the Shapley supercluster, which was an initial suspect. The pull is coming from a region of space that, from our perspective, appears to be eerily empty. It's a void. This deepens the enigma exponentially. We are not being pulled toward a concentration of mass we can detect. We are being pulled toward an apparent nothingness, which by the laws of physics is impossible. The only logical conclusion is that the source of this attraction must reside in the unobservable universe, a realm forever hidden from our view by the finite speed of light and the accelerating expansion of space. This means the structure exerting this pull is not just huge, it must be a cosmic entity on a scale that dwarfs our entire observable universe, a gravitational anomaly so vast it redefines the word immense. This discovery didn't happen overnight. It was a gradual process, a puzzle pieced together over years, born from the meticulous analysis of data from one of the most important telescopes ever launched, the Wilkinson Microwave Anisotropy Probe, or WMAP. Launched in 2001, WMAP mission was to map the cosmic microwave background with unprecedented precision, creating a baby picture of the universe. It was in this incredibly detailed map that the first subtle, strange hints appeared. A team led by astrophysicist Alexander Kashlinsky was studying the kineticsunyaev-zeldovich effect, the very method we described earlier, looking for the expected random, small-scale motions of galaxy clusters. But the signal they found was different. It was a whisper of something larger, a faint but consistent dipole pattern suggesting a shared motion on a scale that was deeply unsettling. The initial reaction from the broader cosmological community was understandably profound skepticism. The finding was so extraordinary that it demanded extraordinary evidence. Could this signal be an artifact, a systematic error in the data processing? Perhaps an unaccounted for foreground contamination from our own Milky Way galaxy. Kashlinsky and his team spent years methodically checking and rechecking their work, ruling out one potential source of error after another. The signal persisted. The skepticism, however, also persisted, acting as a necessary and healthy part of the scientific process. It forced a rigor that would ultimately make the case stronger. The true turning point came with the next generation of data. The Planck Space Telescope, launched in 2009, provided an even more sensitive and higher resolution map of the cosmic microwave background. If the dark flow was an illusion, Planck's superior data would reveal it. Instead, it confirmed it. the coherent flow was still there, and further studies expanded the catalogue of galaxy clusters used in the analysis from hundreds to many thousands. With this richer dataset, the statistical significance of the finding grew. It wasn't just a few clusters moving together, it was a vast swath of the observable universe participating in this mysterious journey. The timeline of discovery, from those first tentative hints in WMAP data to the more robust confirmation from Planck, represents a classic scientific narrative, an unexpected anomaly, intense scrutiny and doubt, and the gradual, stubborn accumulation of evidence that forces us to confront a new and startling reality. This notion of a hidden source of gravity pulling us toward the void immediately brings to mind another famous cosmic mystery, the Great Attractor. Discovered decades ago, this gravitational anomaly also lies in the general direction of the Centaurus constellation, pulling our own Milky Way and thousands of other galaxies toward it with immense force. At first glance, it seems like a perfect solution. Perhaps dark flow is simply the extended influence of this known phenomenon. But when we look closer, the connection unravels, revealing a puzzle that is far more complex and profound. The Great Attractor is a gravitational focal point located about 250 million light-years away. It's a genuine, massive concentration of matter, though much of it is obscured from our view by the dense band of stars and dust in our own galaxy's plane and region we call the zone of avoidance. Over time, with infrared and X-ray telescopes peering through the cosmic dust, we've begun to map the structures there, finding immense galaxy clusters like the Norma cluster that account for at least some of its incredible pull. It is a colossal structure, but it is a structure within our observable universe, governed by the same laws and made of the same stuff as everything else we can see. Dark flow is something else entirely. The galaxy clusters exhibiting this coherent motion are not just nearby, they are spread across billions of light-years, far beyond the reach of the Great Attractor's influence. The gravitational pull from any object weakens dramatically with distance. For the Great Attractor to have any effect on galaxies so immensely far away, it would have to be orders of magnitude more massive than it is, which the observations simply do not support. The dark flow motion is also far more uniform and directed than the local streaming toward the Great Attractor. It's the difference between a river being pulled by a local magnet and the entire ocean being tilted by a slope we cannot see. So if they are not the same thing, could they be related? One compelling theory suggests they might be part of a much larger cosmic hierarchy. Imagine a series of gravitational currents flowing through the universe. The Great Attractor could be a major whirlpool in that current, a large concentration of mass that we can detect. But dark flow might be the evidence of the ocean's underlying current itself, pulling that whirlpool and everything else toward an ultimate source far beyond our horizon. In this view, the Great Attractor isn't the destination. It's merely another passenger on this vast cosmic journey, also caught in the flow toward something infinitely larger and more mysterious. This potential connection deepens the enigma rather than solving it. It suggests that the structures we can see, as immense as they are, might only be local features within a cosmic landscape of unimaginable scale. The pull we feel from the Great Attractor might just be the nearest ripple from a disturbance originating in the unobservable universe. This transforms our understanding from a search for a single missing object to a realization that the entire architecture of the cosmos might be organized on a scale that completely dwarfs our own observable patch, with dark flow serving as our first and only glimpse into that grander design. This leads us to the fifth and perhaps most profound mystery, a concept that stretches the limits of cosmology itself. The source of the dark flow must lie beyond the observable universe. Think about what that truly means. The observable universe is the sphere of space from which light has had time to reach us since the Big Bang, a domain nearly 94 billion light-years across, containing hundreds of billions of galaxies. It is the entirety of everything we can ever hope to see, the ultimate limit of our vision. And yet, the dark flow tells us that this entire colossal expanse, everything we know and will ever know, is being moved by something outside of it. This idea fundamentally challenges one of cosmology's core principles, the cosmological principle. This principle states that on the largest scales, the universe is homogeneous and isotropic. It should look roughly the same in every direction and have no center or edge. The existence of a gravitational pull from a specific point beyond our horizon directly violates this. It suggests that the universe on the grandest scale is not uniform at all. Instead, it may be lumpy and structured, with variations in density and gravity so vast that our entire observable cosmos is just a small part of a much larger and likely very different cosmic landscape. What could possibly exert such an influence? The possibilities are as staggering as they are bizarre. One compelling theory posits the existence of a supermassive structure in the unobservable universe, a concentration of matter and energy so immense it makes our largest superclusters look like specks of dust. This isn't just a bigger version of something we know. It would be a class of object entirely new to physics, a gravitational anomaly on a scale we have no precedent for. Its gravitational field would be so powerful that it warps the fabric of spacetime across billions of light years, pulling on galaxies like a cosmic magnet. Another, even more radical idea is that this pull isn't from a structure within our own universe at all, but from another universe entirely. This ventures into the realm of multiverse theory. In some models of cosmic inflation, our universe is just one bubble in a vast, frothing sea of eternally inflating space-time, with other bubble universes constantly forming. If another of these bubbles existed extremely close to ours in a higher dimensional space, its gravity could potentially leak into our own cosmos, creating a directional pull that we perceive as the dark flow. We would be feeling the gravitational breath of a separate reality, a neighbor we can never visit and never see, but whose presence we can indirectly detect. This transforms our understanding of reality. We are no longer just inhabitants of a universe. We may be citizens of a multiverse, our cosmic journey influenced by forces from realms beyond our own. The dark flow becomes our first tangible, measurable hint that there is something more, a reality beyond the horizon of our observation, forever hidden by the ultimate speed limit of light and the relentless expansion of space. It is a profound and humbling reminder that our view of the cosmos, for all its grandeur, might be incredibly provincial. We are like sailors on a vast ocean, feeling a powerful current but unable to see the distant continent that is its source, left only with the undeniable evidence of its pull. To uncover this celestial current, scientists turn to the oldest light in existence, the cosmic microwave background. This faint glow, a remnant from when the universe was just 380,000 years old, serves as the ultimate fixed background against which all motion can be measured. It is the foundational canvas of the cosmos. Researchers meticulously analyze subtle temperature variations in this radiation, tiny fluctuations that represent the seeds of all future structure, from galaxies to superclusters. But within these minute imperfections, they also hunt for a specific, more dynamic signature, the telltale marks left by massive objects moving through space. The key to this detective work is a complex physical process called the kineticsunyaev-zeldovich effect. Here's how it works in simpler terms. Imagine the cosmic microwave background as a uniform, cold mist filling all of space. Now picture a gigantic galaxy cluster sailing through this mist. The cluster is incredibly hot, filled with superheated gas. As the electrons in this hot gas interact with the photons, the individual particles of light that make up the cosmic microwave background, they give them a slight energy boost. This interaction doesn't create new light. Instead, it slightly alters the energy of the ancient light passing through the cluster. If the cluster were sitting perfectly still relative to the background radiation, this effect would create a specific, symmetrical pattern in the temperature data. However, if the cluster is in motion, it creates a distortion. It's analogous to the Doppler effect we experience with sound. A police siren sounds higher pitched as it moves toward you and lower pitched as it moves away. For light, motion toward an observer makes it appear slightly hotter or bluer, while motion away makes it appear slightly cooler or redder. When a moving galaxy cluster scatters the cosmic microwave background photons, it imprints a specific asymmetric pattern onto the temperature map, a cold spot in the direction the cluster is coming from and a hot spot in the direction it is heading. By carefully measuring the precise shift between these hot and cold spots for thousands of clusters, scientists can calculate not only if they are moving, but their exact velocity and direction. The expectation was always that these motions would be random. Each cluster should be dancing to the tune of its own local gravitational influences, the pull of a neighboring supercluster here, the push from a void there. The initial findings, however, told a completely different story. Instead of a chaotic symphony of individual movements, the data revealed a startling chord. Cluster after cluster across vast distances showed a statistically significant velocity component, all pointing in the same direction. It was as if every single one of these immense structures was caught in the same cosmic river, all flowing toward the constellation Centaurus. The temperature patterns in the ancient light weren't just recording motion, they were mapping a current flowing through the entire observable universe. This evidence, etched into the faint afterglow of creation itself, is what transformed dark flow from a theoretical possibility into an empirical puzzle. The cosmic microwave background, a snapshot of the universe in its infancy, holds within its subtle patterns a clue to a motion happening today, suggesting that the forces shaping our cosmos operate on a scale far grander than we ever imagined. The sheer velocity attributed to this cosmic current is perhaps its most contentious feature. The initial estimates were nothing short of breathtaking, suggesting galaxy clusters were being swept along at speeds between 600 and 1,000 kilometers per second. To grasp what that means, consider this. Our entire solar system orbits the center of the Milky Way at a respectable 220 kilometers per second. The dark flow at its highest estimates would be moving clusters nearly 5 times faster than that, a velocity that defies conventional gravitational explanations on such a colossal scale. This isn't just a gentle drift, it's a cosmic hurricane, and its very existence hinges on the accuracy of these speed measurements. The debate over these numbers is not a simple disagreement. It strikes at the very heart of how we measure the universe. The primary tool for this investigation, as we've discussed, is the kineticsunyaev-zeldovich effect. But extracting a clean signal from this data is an astronomically difficult task. Scientists must perform a delicate operation, subtracting all the known foregrounds, the light from our own galaxy, the emissions from other distant galaxies, and the intrinsic noise of the instruments themselves, to isolate the specific temperature distortion caused by the moving clusters. It's like trying to hear a single, faint whisper in a roaring stadium by carefully canceling out every other sound. Critics of the high-velocity claims argue that even the smallest unaccounted for systematic error in this subtraction process could create a false signal that mimics the signature of a bulk flow. Different research groups using slightly different methodologies and datasets have arrived at wildly different conclusions. Some analyses, particularly those using data from the Planck satellite, have reported a much more modest flow, or in some cases, no statistically significant bulk motion at all beyond what the standard model allows. These teams point to potential contaminants, suggesting that the signal could be an artifact of how we map the cosmic microwave background itself, or an incomplete model of our own galaxy's dust emissions. The central question becomes, are we measuring a real motion of the universe, or are we measuring the limitations of our own technology and models? Proponents of the dark flow hypothesis counter that these criticisms have been meticulously addressed. They argue that the teams reporting null results are often using different statistical techniques or cluster catalogs that might inadvertently smooth out or mask the coherent signal. They maintain that when the data is processed with their specific, refined methods, the signal of a high-velocity flow not only persists but strengthens. This isn't a case of one side being right and the other wrong. It's a classic scientific frontier where the cutting edge is often messy and uncertain. The controversy itself is a healthy and necessary part of the process, driving every team to refine their methods and challenge their assumptions in the quest for an undeniable truth. Ultimately, the velocity controversy is more than a technical debate about kilometers per second. It is a struggle to interpret the faintest whispers from the edge of our knowledge. The incredible speed is what makes dark flow so revolutionary. A slow drift could perhaps be explained by a known, if unseen, structure within our universe. But a flow approaching 1,000 kilometers per second almost certainly requires a cause from beyond our cosmological horizon, a gravitational source of unimaginable power. Therefore, the resolution of this debate will determine far more than just a number. It will either validate our current model of the cosmos or force us to seriously consider that we are living in a very special and very peculiar part of a much larger and stranger reality. While the idea of a pull from beyond the horizon is the most dramatic explanation, it is not the only one on the table. The scientific process demands that extraordinary claims be met with rigorous skepticism, and many researchers have proposed alternative theories that seek to explain dark flow within the known confines of physics, or at least without requiring a universe beyond our own. These competing ideas fall into several fascinating categories, each offering a different lens through which to view the data. One prominent line of thinking challenges the very laws we use to interpret the cosmos, gravity itself. Our entire understanding of cosmic motion is built upon Einstein's theory of general relativity, which has been spectacularly successful for over a century. But what if, on the very largest scales, this theory needs tweaking? Modified Newtonian dynamics, or MUND, and its relativistic extensions propose that gravity behaves differently when it becomes incredibly weak, such as in the vast voids between galaxy clusters. Proponents of these models suggest that dark flow might not be a real motion at all, but rather an illusion created by our misunderstanding of how gravity operates over billions of light years. In this view, the apparent coherent flow could be a signature of gravity's subtle changes at extreme distances, removing the need for a hidden, colossal source of mass. However, these modified gravity theories remain highly controversial and often struggle to explain all cosmological observations as elegantly as the standard model, leaving them as intriguing but unproven possibilities. A more conservative and perhaps more likely alternative is that the signal is not cosmological but instrumental. This explanation points the finger not at the universe but at our own methods of observing it. The detection of dark flow relies on an incredibly complex and delicate process of subtracting foreground noise from the cosmic microwave background data. Critics argue that even a tiny, unaccounted for systematic error could create a false dipole pattern that mimics a bulk flow. This error could stem from an incomplete model of our own Milky Way's emissions, subtle biases in how the telescope's instruments were calibrated, or an oversimplification in the way we map the distribution of hot gas within the distant galaxy clusters themselves. If this is the case, then dark flow becomes a monument to our own limitations, a ghost in the machine of our most advanced technology, reminding us that our view of the cosmos is always filtered through the lens of our own imperfect instruments. Between these two extremes lies a third possibility, that the flow is real, but its source is not beyond the horizon. Perhaps there exists within our observable universe a structure so immense, so unimaginably large, that we have simply not mapped it yet. We already know the cosmos is structured in a cosmic web of filaments, clusters, and superclusters. What if there is a tier above even the superclusters? A hypercluster, or a gravitational anomaly on a scale we haven't previously conceived, pulling on everything within its vast reach. This would be a structure spanning billions of light years, so large that we are inside of it and cannot easily see its shape, much like a fish cannot see the entirety of the ocean. Its gravitational influence would be pervasive, creating a coherent flow that appears to come from a single direction. The challenge for this theory is that such a structure would itself violate the cosmological principle, and our large-scale surveys haven't found evidence for anything of such staggering proportions. Yet the possibility remains that we just haven't looked in the right way, or that this structure is so diffuse it has eluded detection. Each of these alternatives represents a different bet on the nature of our universe and our place within it. The modified gravity hypothesis bets on a fundamental revolution in physics. The systematic error explanation bets on the fallibility of our own technology and methods. And the unseen large-scale structure theory bets on the existence of a hidden colossus within our own cosmic backyard. What makes dark flow such a compelling mystery is that, for now, no single explanation has definitively won the day. The debate itself is a vibrant and essential part of the scientific process, a collective effort to stress-test our understanding of reality from every possible angle. Whether the final answer lies in rewriting physics, refining our instruments, or discovering a new class of cosmic structure, the journey to solve this puzzle is guaranteed to deepen our knowledge of the cosmos in profound and unexpected ways. The launch of the Planck Space Telescope in 2009 represented a quantum leap in our ability to peer into the cosmic dawn. With sensitivity and resolution far surpassing its predecessor, WMAP, Planck was poised to be the ultimate arbiter in the dark flow debate. Its mission was to map the cosmic microwave background with such exquisite detail that it would either solidify the standard model of cosmology or reveal its flaws. When it turned its gaze toward the mystery of the bulk flow, the results were not a simple confirmation or denial, but a fascinating and complex twist that deepened the intrigue. Planck's data did, in fact, corroborate the core finding, a persistent, large-scale flow of galaxy clusters. This was a crucial validation. The signal was not an artifact of WMAP's instrumentation. It was a real feature of the universe that persisted even under Planck's sharper scrutiny. However, the new data also refined the measurements, and in doing so, presented a new set of puzzles. Planck's analysis suggested the flow might be slightly slower and might not extend to quite as great a distance as some of the more dramatic initial claims. While still significant and inexplicable by standard cosmology, these revised parameters forced a recalibration of the phenomenon's scale and power. But the most profound complication from Planck came from what it saw, or rather, what it didn't see. The satellite provided the most precise map ever made of the cosmic microwave background, and scientists immediately used it to search for any secondary imprint that the source of the dark flow might have left on this ancient light. The logic was compelling. If a supermassive structure beyond our horizon was pulling on millions of galaxies, its immense gravitational power might also have warped the fabric of spacetime on a colossal scale, creating a detectable signal in the form of a specific pattern in the microwave background. Researchers searched for this telltale sign, a ghostly fingerprint of the unseen attractor. Yet, despite its incredible sensitivity, Planck found nothing. No unusual patterns, no giant cosmic wake, no evidence of a gravitational titan lurking in the unobservable darkness. This null result is arguably as mysterious as the flow itself. It creates a tantalizing paradox. We have strong, replicated evidence that something is pulling a vast swath of the universe in a specific direction. Yet our most powerful instrument can find no direct evidence of the puller. This forces us to confront several unsettling possibilities. Perhaps the source is even farther away than we thought, so distant that its gravitational influence travels to us, but its imprint on the ancient light is too faint even for Planck to detect. Or maybe its nature is something we haven't even conceived of, an entity that exerts gravitational influence without creating the specific space-time distortions we know how to look for. It could be that the structure is not a single, dense object, but something vastly more extended and diffuse, like a gravitational gradient across the multiverse, which would leave a much subtler signature. The Planck mission, therefore, did not close the book on dark flow. It opened a new and more sophisticated chapter. It transformed the mystery from a simple question of, is it real, to a far more nuanced inquiry into what could possibly cause an effect we can measure but cannot directly see. The satellite provided the best evidence yet that we are caught in a cosmic current, while simultaneously deepening the void into which that current flows, leaving us with a confirmed phenomenon and a more profound absence of explanation. Could dark flow be a clue that we are fundamentally misunderstanding dark energy itself? This mysterious force, making up about 68% of the universe, is responsible for its accelerating expansion, relentlessly pushing galaxies apart. Dark flow, in stark contrast, is a story of pull, of a mysterious gravitational attraction. They appear to be opposing forces, one an expansive pressure and the other a contractive tug. Yet, some theorists propose that this very opposition might be an illusion, and that these two great cosmic mysteries could be two sides of the same coin, deeply intertwined in a way we have yet to comprehend. The Standard Model treats dark energy as a uniform, homogeneous force, a property of space itself that is constant everywhere. This is embodied in Einstein's cosmological constant. But what if dark energy isn't uniform? This is a radical departure known as the quintessence model, where dark energy could be a dynamic field that varies in strength and density across space and time. In such a model, regions of weaker dark energy would offer less resistance to gravity. Imagine a vast, invisible landscape where the repulsive force of dark energy has hills and valleys. A massive valley, a region where dark energy is significantly weaker, would create a relative gravitational sink. The normal pull of matter would dominate more easily in this area, potentially drawing everything toward it. From our perspective, this would look exactly like a gravitational attraction from a specific point, a dark flow. In this scenario, we aren't being pulled by an unseen mass. We are being pushed less from one direction because the dark energy there is weaker, creating a net motion toward that void. This idea flips the script entirely. The source of dark flow might not be a colossal concentration of mass, but a profound absence of repulsive energy. It transforms the mystery from searching for a hidden gravitational titan to searching for an explanation of why the fundamental fabric of reality might be lumpy and inconsistent on the grandest scales. This would be a revolution in cosmology, challenging the very notion that the laws of physics are the same everywhere. If dark energy can vary, then our entire universe might be far more textured and unpredictable than we ever imagined. Another, even more speculative, connection involves the very nature of space-time. Some cutting-edge theories suggest that dark energy and gravity might not be independent forces but could emerge from a more fundamental, underlying principle of the universe. In these models, the accelerating expansion and a large-scale flow could be linked manifestations of this deeper physics. For instance, if the fabric of space-time itself has a preferred direction or structure at the quantum level, a concept that is purely theoretical but not impossible, it could simultaneously drive the overall expansion and create a subtle directional flow within it. We would be observing two different symptoms of the same underlying cosmic condition. The challenge, of course, is that all of these ideas currently reside in the realm of theoretical possibility. They are compelling narratives that fit the available data, but they lack direct, testable evidence. This is the frustrating beauty of frontier science. Dark flow and dark energy are two of the greatest puzzles in modern cosmology, and the mere suggestion that they might be connected opens up a dizzying array of possibilities, each more profound than the last. It forces us to ask not just what is causing these effects, but whether we are even asking the right questions about the fundamental forces that shape our reality. The interaction between these two mysteries suggests that our current model of the universe, for all its success, might be a simplified version of a far more complex and bizarre cosmic truth. This cosmic current doesn't just challenge our map of the universe, it threatens to unravel one of the most fundamental numbers in all of cosmology, the Hubble constant. This crucial value represents the rate at which the universe is expanding today, the current speed of the cosmic acceleration kicked off by the Big Bang. For decades, astronomers have worked to pin down this number with ever-increasing precision, using a variety of methods. Yet a stubborn and growing discrepancy has emerged, a tension between how fast the early universe tells us it should be expanding and how fast we actually observe it expanding now. Intriguingly, the measurements of dark flow are now wading directly into this debate, not as a bystander but as a potential instigator. The conflict known as the Hubble tension is a tale of two measurement techniques. One method looks at the very early universe using the detailed snapshot of the cosmic microwave background from the Planck satellite. By studying the subtle fluctuations in this ancient light, cosmologists can calculate what the Hubble constant should be based on our standard model of the universe's evolution. This is often called the early universe measurement. The other method looks at the late universe, using relatively nearby objects like Cepheid variable stars and Type Ia supernovas. These act as standard candles, objects whose intrinsic brightness we know, allowing us to measure their distance, and by comparing that to how fast they are moving away from us, we can directly calculate the current expansion rate. The problem is stark. These two methods, both exquisitely precise, give answers that disagree by a small but statistically significant margin. The late universe appears to be expanding faster than the early universe says it should be. This is where dark flow enters the stage, not with a solution but with a fascinating complication. The very technique used to detect the bulk flow relies on the cosmic microwave background as a stationary reference frame. We measure how fast galaxy clusters are moving against this fixed backdrop, but this calculation is deeply intertwined with our understanding of the Hubble flow, the general expansion of the universe. If our value for the Hubble constant is incorrect, it could introduce a systematic error into the dark flow measurements. Conversely, if dark flow is a real and powerful phenomenon, it could itself be the source of the error in our local measurements of the Hubble constant. Imagine you're trying to measure the speed of a river's current by timing how fast a leaf floats by. Your calculation would be thrown off if you didn't realize the entire riverbank you were standing on was also slowly sliding downstream. In this analogy, the leaf is a distant supernova used to measure cosmic expansion, and the sliding riverbank is the dark flow. Our local region of space, including the galaxies we use as standard candles, might itself be caught in this vast current. This means when we measure a galaxy's velocity, we are not just measuring the pure Hubble expansion. We are measuring that expansion plus any additional velocity from this mysterious bulk flow. If we fail to account for this extra component of motion, we would overestimate the Hubble constant. The measured tension, the unexpectedly fast expansion, could partially be a phantom signal, an illusion created by our own motion within a larger cosmic stream. This creates a deeply complex chicken and egg problem for cosmologists. Is the Hubble tension causing us to miscalculate the properties of dark flow? Or is dark flow itself the hidden variable causing the Hubble tension? Untangling this requires an incredible feat of cosmological deduction. Some researchers are now building new models that attempt to incorporate both phenomena. They explore whether a large-scale flow, perhaps driven by a beyond-the-horizon structure, could impart just enough extra velocity to our local standard candles to explain the discrepancy in the Hubble constant measurements. It's a radical idea that one of the greatest mysteries in modern cosmology might be explained, at least in part, by another. This doesn't just add a new layer to the dark flow enigma. It elevates it from a curious anomaly to a potential keystone in the arch of our understanding, a force significant enough to distort our perception of the universe's most fundamental rate of change. This possibility catapults us from the familiar terrain of our own universe into the profoundly speculative realm of the multiverse. If the source of the dark flow is truly beyond our cosmological horizon, then the most extraordinary explanation is that its pull is not from a structure within our own cosmos at all, but from an entirely separate universe. This isn't just a shift in scale, it's a fundamental redefinition of reality, suggesting our universe is but one bubble in a vast, frothing cosmic foam. The theoretical framework for this idea often ties back to the theory of eternal inflation. This model proposes that the rapid expansion of space-time that occurred just after the Big Bang, known as inflation, never truly stopped. Instead, it continues eternally in a background state. Within this eternally inflating space-time, random quantum fluctuations can cause pockets to stop inflating and instead pinch off to form their own distinct bubble universes, each with its own unique laws of physics. Our universe would be one such bubble. Crucially, these bubbles are not entirely isolated. They are embedded within the inflating background, and in some models they can interact or at least come close enough to feel each other's influence. Gravity, according to Einstein's theory, is the warping of spacetime itself. If another bubble universe formed extremely close to ours in this higher dimensional inflating background, its sheer mass, the entire weight of another cosmos, could create a gravitational dent in the fabric of spacetime that we, inside our bubble, could perceive. We wouldn't see the other universe. The light from it could never cross the inflating barrier between us. But gravity, if it behaves as theorized, might be able to leak across this divide. The dark flow in this scenario would be the gravitational wake of our cosmic neighbor, a phantom wind from a shore we can never reach, gently tugging our entire observable universe in its direction. The implications of this are staggering. It would be the first empirical evidence, however indirect, for the existence of a multiverse. Cosmology would shift from studying a single, isolated universe to studying our universe's place within a much larger and likely very diverse cosmological ecosystem. We would have to consider that the fundamental constants we hold so dear, the strength of gravity, the mass of an electron, might not be universal laws but merely local bylaws, the unique outcome of how our particular bubble formed. The pull we feel could be from a universe where gravity is 1,000 times stronger, or where nuclear forces never congealed matter into stars, making it an unfathomably dense and alien place. Naturally, this interpretation is met with intense skepticism, and rightly so. It pushes the boundaries of what is scientifically testable. How can we ever confirm the existence of something that is, by its very definition, outside our universe and forever beyond our observation? Critics argue that invoking other universes is a convenient way to explain away any anomaly without providing falsifiable evidence, potentially placing it outside the realm of science altogether. Proponents counter that the gravitational effect itself is the evidence, a measurable anomaly that finds its most natural explanation within a well-developed, if speculative, theoretical framework. They suggest that as we refine our models of the early universe and the nature of gravity, we might find other, subtler signatures that a multiverse would leave behind. Whether the ultimate answer lies in a multiverse or not, the very fact that dark flow forces us to seriously entertain the idea is a testament to its profound mystery. It acts as a gateway, pushing our imagination to the absolute limit and challenging us to consider that the greatest forces shaping our reality may not be contained within the universe we see, but may originate from realms of existence so foreign that their very presence is felt only as a silent, irresistible current in the dark. But to chart this cosmic current, scientists must first choose their signposts, and this selection process itself has become a critical point of debate. The method for detecting dark flow relies on studying specific galaxy clusters, but the universe contains countless such clusters, each with unique properties. Researchers cannot analyze them all, so they must create a catalog, a sample that is both manageable and representative of the whole. The concern is that the criteria used to build these catalogs might inadvertently introduce a bias, a systematic error that creates the illusion of a coherent flow where none exists. This isn't a question of bad science, but rather an inherent challenge of peering into the deepest cosmos, where our tools and methods shape what we are able to see. A primary criterion for selection has traditionally been X-ray brightness. A galaxy cluster is filled with incredibly hot gas, and this gas emits copious amounts of X-ray radiation. The brighter a cluster glows in X-rays, the more massive it is assumed to be. This makes intuitive sense. A bigger, heavier cluster contains more hot gas and should shine more brilliantly. These bright, massive clusters are the ideal targets for the kineticsunyaev-zeldovich effect study because the signal they imprint on the cosmic microwave background is stronger and easier to measure against the noise. So, researchers naturally gravitate toward creating catalogs of the most X-ray luminous clusters they can find, as these offer the clearest data. However, this preference for the brightest and most massive clusters might be painting a misleading picture of cosmic motion. Imagine you're trying to understand the flow of a river by tossing in a bunch of different objects, some large, heavy logs and some small, light twigs. If you only ever measure the speed of the large logs, you might get a very consistent reading because their size makes them resistant to small eddies and cross-currents. But if you measured the twigs, you might find their paths are more chaotic, influenced by every tiny ripple. In this analogy, the X-ray bright clusters are the large logs. Their great mass means their motion is primarily governed by the largest scale gravitational forces, making them excellent tracers for a bulk flow. But by focusing almost exclusively on them, are we missing the more complicated story told by the smaller clusters? If smaller, fainter clusters showed a more random pattern of motion, it would suggest the dark flow is not a universal current affecting all matter, but perhaps a phenomenon that only the most massive structures are sensitive to, which would be a crucial distinction. The potential bias goes even deeper. A cluster's X-ray luminosity isn't just about its mass, it's also influenced by the density and temperature of its gas. Two clusters of identical mass could have different X-ray brightness if one is more compact than the other. Furthermore, the process of measuring the kineticsunyaev-zeldovich effect itself involves assumptions about the physical conditions inside the cluster, such as the density and temperature profiles of the hot gas. If these assumptions are slightly off for certain types of clusters, it could lead to a systematic miscalculation of their velocity. If that miscalculation happens to correlate with the direction on the sky, for instance, if clusters in the direction of Centaurus are systematically different in some subtle way that affects the measurement, it could artificially create the signal of a coherent flow. Critics of the dark flow hypothesis argue that this cluster selection effect is a far more likely explanation than a pull from another universe. They suggest that the teams who find a strong signal may have inadvertently curated a catalog where the selected cluster's properties and the measurement techniques combine to produce a false dipole. Proponents, on the other hand, have worked diligently to address these concerns. They have expanded their catalogs to include thousands of clusters, not just the very brightest, and have employed increasingly sophisticated models to account for the internal physics of each cluster. They argue that as their methods have improved, the signal has not vanished but has instead become more robust. This ongoing methodological refinement is the essential, if unglamorous, work of cosmology. It's a painstaking process of questioning every assumption, testing every potential bias, and slowly closing the loopholes until only the most compelling explanations remain. The selection effect debate ensures that the case for dark flow is being stress-tested from every possible angle, making any eventual confirmation all the more powerful. At the heart of this entire cosmic detective story lies a remarkably clever, albeit complex, piece of physics known as the kineticsunyaev-zeldovich effect. It's the fundamental tool that allows us to see the unseen motion of galaxy clusters, and understanding how it works is key to appreciating the evidence for dark flow. The principle itself is a beautiful blend of simple concepts and profound implications, all centered on the oldest light in the universe. Think of the cosmic microwave background as a uniform, cold sea of radiation that fills every corner of space, a relic from a time when the universe was a scorching hot plasma. Now imagine a massive galaxy cluster sailing through this sea. This cluster isn't empty. It's filled with an incredibly hot, thin gas, so hot that its electrons are whizzing around at nearly the speed of light. As these fast-moving electrons in the cluster's gas encounter the individual photons, the particles of light, that make up the cosmic microwave background, they don't just let them pass by undisturbed. They collide, and in doing so, the electrons transfer a tiny bit of their immense energy to the much colder, ancient photons. If the cluster were perfectly stationary, this interaction would create a very specific, symmetric distortion in the background radiation. It would make the microwaves appear slightly hotter or more energetic in a symmetrical pattern around the cluster. This is the thermal Sunyaev-zeldovich effect, and it's a powerful way to find and study these massive structures. But the kinetic effect is different. It comes into play when the entire cluster is in motion relative to the static background of the cosmic microwave background. This motion adds a critical new ingredient, the Doppler shift. We're all familiar with the Doppler effect with sound, how the pitch of a siren seems higher as an ambulance races toward you and lower as it speeds away. Light behaves in a similar way. When a light source moves toward you, its waves are compressed, making it appear slightly bluer and more energetic, which for microwaves translates to a tiny increase in temperature. When it moves away, the waves are stretched, making it appear redder and cooler. Now combine this with the energy boost from the hot electrons. As the moving cluster scatters the cosmic microwave background photons, it doesn't do so symmetrically. It creates a distinct asymmetric pattern, a slight hot spot in the direction the cluster is moving and a slight cold spot in the direction it's coming from. Detecting this incredibly subtle imbalance is the heart of the method. By meticulously measuring the precise difference in temperature between the hot and cold spots imprinted on the microwave background by a cluster, astronomers can calculate its velocity along our line of sight. It's an astronomical speed gun, measuring not just whether a cluster is moving, but exactly how fast and in which direction. The sheer difficulty of this measurement cannot be overstated. The temperature shifts involved are minuscule, on the order of millionths of a degree, buried within an already faint signal that itself is obscured by foreground radiation from our own galaxy. Isolating this specific signature requires exquisitely sensitive instruments and incredibly sophisticated data processing to subtract all other possible sources of contamination. The original expectation was that when this was done for thousands of clusters across the sky, the resulting map of motions would show a random, chaotic jumble. Each cluster should be responding to the gravitational tug of war in its own local neighborhood, pulled this way and that by nearby superclusters and void. The profound shock was that the data revealed something entirely different. Instead of randomness, there was a startling coherence. A significant number of these immense structures, scattered across billions of light years, showed a shared velocity component, all contributing to a collective stream in one particular direction. The kineticsunyaev-zeldovich effect didn't just reveal motion. It unveiled a current flowing through the cosmos, a silent testimony written in the distorted whispers of the universe's first light. This mysterious flow of galaxies toward an unseen attractor forces us to reconsider the very architecture of the cosmos on its grandest scales. Could dark flow be connected to other colossal and puzzling structures that challenge our understanding of the universe's formation? Astronomers have mapped the cosmic web and found it contains not just filaments and voids, but genuine anomalies, structures so vast they seemingly defy the theoretical size limit of the universe. The most famous of these is the Hercules Corona Borealis Great Wall, a gigantic concentration of galaxies stretching over 10 billion light-years. To grasp that scale, consider that our entire observable universe is about 93 billion light-years across. This single structure occupies more than a tenth of that distance. According to our standard models of cosmology, such a colossal formation should not exist. The principle of isotropy suggests that matter should be distributed fairly evenly across the universe once you zoom out far enough. But the Great Wall is a glaring exception, a cosmic continent that breaks all the rules. Then there is the enigmatic CMB cold spot, a vast and unusually cold region in the cosmic microwave background, first spotted by the WMAP satellite and later confirmed by Planck. This isn't just a slightly cooler patch, it's a massive void, a sphere of space about 1 billion light-years across that appears to be significantly emptier than it should be. One leading theory to explain its profound coldness is that it might be a supervoid, a region of such incredibly low density that photons of light traveling through it lose a tiny amount of energy as they climb out of its weakened gravitational well, a phenomenon known as the integrated Sachs-Wolf effect. But there's a problem. The observed cold spot is far colder than even the largest known void should be able to produce. This has led to more exotic explanations, including the mind-bending possibility that it is a bruise left from a collision with another universe during the early inflationary period. Now consider the placement of these mysteries relative to the dark flow. The direction of the flow toward Centaurus and the location of these other anomalies might not be a mere coincidence. Could the gravitational pull responsible for the dark flow be originating from a region of space that also contains these impossible structures? Perhaps the Hercules Corona Borealis Great Wall is not the end of the story, but merely the nearest edge of something even more immense, a gravitational anomaly on a scale we can scarcely conceive, whose full extent lies mostly in the unobservable universe. Its incredible mass would naturally pull galaxies toward it, creating the dark flow, while its sheer size and density would account for the existence of a structure that breaks the cosmological size limit. In this scenario, the Great Wall we see is just the visible tip of a hidden cosmic iceberg. The cold spot presents a different but equally fascinating potential connection. If this void is indeed a sign of a collision with another universe, it provides a direct physical mechanism for the multiverse explanation of dark flow. The gravitational pull we feel could be the lingering influence of that other universe, its gravity still tugging on ours long after the initial collision. Alternatively, the cold spot might not be a void at all, but the shadow cast by the very structure causing the dark flow. If an unimaginably dense and vast concentration of matter lies between us and the cosmic microwave background, it could potentially gravitationally lens the light, distorting and cooling the CMB in that specific region and creating the cold spot we observe, while its gravity simultaneously pulls millions of galaxies in its direction. These aren't mutually exclusive ideas. They could be different facets of the same profound cosmic truth. The existence of these multiple, seemingly impossible large-scale structures suggests that our universe is far less uniform and far more strangely structured than the standard model allows. Dark flow might not be an isolated mystery, but rather the most dynamic piece of evidence in a much larger puzzle, pointing toward a cosmos filled with architectural wonders and gravitational giants that we are only just beginning to sense. If the dark flow is a real and persistent feature of our cosmos, its behavior over time could be one of our most powerful diagnostic tools, a way to peer into the very nature of its mysterious source. This leads us to a pivotal question. Has this cosmic current always been there, flowing at the same strength and in the same direction? Or has it evolved, ebbing and flowing over the billions of years since the Big Bang? By looking out into space, we are also looking back in time. The light from a galaxy 1 billion light-years away shows us how it looked 1 billion years ago. This principle allows astronomers to effectively construct a timeline of the dark flow, observing how its properties might have changed across different cosmic epochs. The method for investigating this is both simple in concept and staggeringly complex in execution. It involves dividing the vast catalogue of galaxy clusters used in dark flow studies not just by their direction in the sky, but by their distance from us. By analyzing clusters that are, for instance, 5 billion light-years away separately from those that are 1 billion light-years away, researchers can compare the flow's characteristics in the ancient universe to its behavior in the more recent universe. A cluster 5 billion light-years away is showing us its motion from 5 billion years in the past, while a nearer cluster reveals its more recent movement. If the flow's speed or direction has shifted significantly between these two snapshots, it would tell a dramatic story about the dynamic nature of the force behind it. Imagine two possible scenarios, each with profound implications. In the first scenario, we find that the dark flow is consistent. Clusters from 5 billion years ago, 3 billion years ago, and today are all moving at roughly the same speed and toward the exact same point in the sky. This stability would be a powerful argument for a fixed, permanent, and incredibly distant source. It would suggest that the gravitational attractor is so colossal and so far beyond our horizon that its pull has remained a constant, dominant force throughout much of cosmic history, like a distant mountain that has always guided a river's course. This would lend strong support to theories involving a permanent feature of the multiverse or a supermassive structure whose influence has been unwavering. Now consider the opposite finding. The dark flow shows clear evolution. Perhaps clusters in the early universe were moving even faster, and the flow has been slowing down over time. This could indicate that the source of the pull is moving away from us, its gravitational influence diminishing as the expansion of the universe increases the distance between us. Alternatively, the direction of the flow might have shifted slightly over billions of years. This would be evidence that the source itself is not fixed, but is also in motion within a larger cosmic framework. Such a discovery would be even more revolutionary, pointing to a dynamic and evolving cause, perhaps the movement of another universe relative to our own or the slow migration of an unimaginably large cosmic structure. The current evidence on this front is tantalizing but not yet conclusive. Some analyses of the data have suggested that the dark flow's strength might indeed be distance-dependent, with a possible weakening of the signal for the most distant clusters. However, these results sit right on the edge of statistical significance, caught in the same web of uncertainty and debate that surrounds the phenomenon itself. Measuring the flow for distant clusters is exponentially more difficult. The signal is fainter, the data noisier, and the potential for systematic errors is greater. Untangling a true evolutionary signal from this observational fog is one of the greatest challenges in modern cosmology. It requires ever larger catalogues of clusters and ever more precise measurements of the cosmic microwave background. The quest to map the timeline of the dark flow is not just about understanding a mystery. It's about learning to read the history of the cosmos in the faintest of whispers, a skill that will define the next era of astronomical discovery. Pushing the boundaries of cosmic knowledge means confronting the harsh limitations of our own technology. Every measurement of the dark flow is an exercise in extracting an almost impossibly faint signal from a roaring ocean of interference, a task that pushes our most advanced instruments to their absolute breaking point. The primary tool for this work is the Space Telescope, designed to observe the cosmic microwave background from a vantage point above Earth's obscuring atmosphere. Yet even these engineering marvels, like the legendary Planck satellite, have fundamental physical constraints. Their resolution is limited by the size of their mirrors and the number of their detectors. This means the sky is mapped in pixels, and each pixel represents a tiny but finite area. The subtle hot and cold spots of the kineticsunyaev-zeldovich effect, the very fingerprints of the dark flow, can be smoothed over or lost entirely if they are smaller than the instrument's pixel size, a process known as beam smearing. It's like trying to read the fine print on a document through a slightly frosted glass. You can see the general shapes, but the crucial details are blurred, forcing scientists to make complex statistical corrections that can themselves introduce uncertainty. Beyond resolution lies the even greater challenge of noise. The signal we are trying to detect is not a clear, strong tone, but a whisper buried in a cacophony. This noise comes from everywhere. There is foreground noise from our own Milky Way galaxy, the shimmering glow of countless stars and the subtle, veiling light emitted by interstellar dust. There is noise from other, more distant galaxies and quasars that pepper the sky with their own microwave emissions. And then there is the inherent instrumental noise, the faint hiss generated by the telescope's own electronics and detectors as they operate in the extreme cold of space. Isolating the specific signal of a galaxy cluster's motion requires a painstaking and imperfect process of subtracting all these known sources of contamination. The concern is always that a tiny, unmodeled feature of our own galaxy's dust, or a subtle systematic error in the instrument's calibration, could mimic the exact dipole pattern that signifies motion. When the target signal is measured in millionths of a degree, even the most minuscule unaccounted-for effect can create a phantom flow or obscure a real one, leaving researchers in a perpetual state of questioning whether they are measuring the universe or merely measuring the limitations of their own exquisite machines. This uncertainty fuels a cycle of intense debate within the cosmology community, a cycle that is both a hallmark of healthy science and a testament to the profound difficulty of the problem. A team using one dataset and a specific statistical pipeline might announce a detection of the flow with high confidence. Shortly thereafter, another team, using a different methodology to process the exact same data or a different catalog of galaxy clusters, might publish a paper arguing the signal is not statistically significant and is likely a remnant of unsubtracted foregrounds. This back and forth isn't a sign of failure. It is the scientific method working as intended, with each group critically scrutinizing the other's assumptions and methods. The very complexity of the analysis means there are numerous decision points: how to select clusters, how to model their gas, how to filter the data, and each choice can lead to a slightly different conclusion. This methodological maze means that the evidence for dark flow is never a simple, incontrovertible fact, but rather a compelling, persistent, and hotly debated anomaly that refuses to be easily dismissed or confirmed, ensuring its status as one of the most tantalizing and frustrating mysteries in modern astronomy. But perhaps the most profound clue hidden within this cosmic current is not about what lies beyond, but about the invisible architecture of our own universe. We've long known that the cosmos is filled with dark matter, an enigmatic substance that outweighs normal matter by a factor of 5 to 1. Its gravitational glue holding galaxies together. Yet, despite its overwhelming presence, dark matter remains utterly invisible, detectable only by its gravitational effects on the things we can see. The standard model assumes this dark matter is distributed in a vast, diffuse halo, roughly following the visible matter but on a much larger scale. Dark flow, however, introduces a startling new possibility. What if dark matter itself is not just a static backdrop, but is also caught in this immense stream, and its very motion is the engine behind the phenomenon we observe? This idea turns our understanding on its head. The coherent motion of galaxy clusters detected through the kineticsunyaev-zeldovich effect is a measurement of normal matter, the hot gas within those clusters. But that normal matter is just the visible tip of a much larger, darker iceberg. Every galaxy cluster is embedded within a massive halo of dark matter that is far more extensive and massive than the cluster itself. For the entire cluster to be moving in a coordinated flow, the immense gravitational field of its dark matter halo must also be moving in lockstep. This suggests that dark flow is not merely a motion of galaxies, but a bulk motion of the entire cosmic infrastructure, including the dark matter scaffolding upon which the visible universe is built. The flow we detect in the hot gas is just the tracer, the smoke indicating the direction of a much larger, invisible wind. If this is true, then dark flow becomes a powerful, if indirect, probe of dark matter's behavior on the very largest scales. It could be revealing that dark matter is not distributed as smoothly and uniformly as we thought. Instead of a homogeneous sea, the dark universe might be structured into colossal rivers and currents, vast streams of invisible particles all flowing in the same direction on a scale of billions of light years. This wouldn't just be clumping, it would be coordinated motion on a truly cosmic scale, a directional preference that flies in the face of the cosmological principle. The source of the dark flow's pull might not be a single massive object, but a gravitational gradient carved into the distribution of dark matter itself, a slope in the invisible landscape of the cosmos down which everything is sliding. This possibility opens a door to understanding one of the most frustrating aspects of dark matter, its nature. Different theoretical candidates for dark matter, from WIMP to actions to sterile neutrinos, would behave in slightly different ways over these immense scales. Some might be more likely to form these vast, coherent streams than others. By carefully mapping the precise details of the dark flow, its speed, its consistency across different distances, and any subtle variations, cosmologists could potentially rule out some dark matter models and lend support to others. The flow becomes a colossal laboratory experiment, testing the properties of the universe's dominant substance under conditions we could never hope to recreate on Earth. The silent, relentless current toward Centaurus may be our best clue yet to unlocking the secret identity of the dark matter that shapes our cosmic fate. As we chart the course of this mysterious current across the cosmos, its unwavering direction toward the constellation Centaurus leads us to another profound and deeply puzzling feature etched into the ancient light of the universe, a pattern so strange that cosmologists have dubbed it the axis of evil. This is not a name born of drama, but of genuine scientific bewilderment. The axis of evil refers to a peculiar and unexpected alignment of the largest scale fluctuations in the cosmic microwave background. According to our standard model, the hot and cold spots in this primordial radiation should be randomly distributed with no preferred direction or orientation. The universe, after all, should have no center and no edge. Yet, when we look at the full sky map from missions like WMAP and Planck, we find that these largest fluctuations appear to be subtly aligned along a specific axis that runs through the universe, a preferred direction that simply should not exist. The connection to dark flow is both immediate and startling. The direction of this cosmic axis, this so-called axis of evil, is not arbitrary. It aligns remarkably well with the direction of the dark flow itself. Think about the profound oddity of this. We have two independent universe-scale anomalies. One is a pattern in the oldest light we can see, a fossil from the birth of the cosmos. The other is a dynamic motion of galaxy clusters happening in the present day. They are separated by nearly 14 billion years of cosmic evolution, and yet they seem to be pointing in the same direction. This is either the most incredible coincidence in the history of astronomy, or it is a monumental clue that these two mysteries share a common underlying cause, a fundamental lopsidedness in the very fabric of our universe. So what could possibly link a pattern in the infant universe to a motion occurring today? One compelling theory suggests that both phenomena could be the result of a primordial gravitational field, a titanic distortion that was imprinted on the cosmos during its first fleeting moments of existence. During the period of inflation, when the universe expanded faster than the speed of light, random quantum fluctuations were stretched to enormous sizes, becoming the seeds for all future structure. But what if something else was stretched as well? If a massive, pre-existing structure, or perhaps a gradient in the energy field driving inflation, existed before the Big Bang, its gravitational influence could have been imprinted on the space-time of our newborn universe. This would have created a preferred direction from the very beginning, a cosmic tilt that affected both the distribution of the first light and set everything within that universe on a specific collective course. This idea ventures into the realm of quantum gravity and theories that attempt to describe the conditions before the Big Bang. In some models, our universe is not a unique creation but one bubble in a wider multiverse. The gravitational pull of a neighboring universe bubble could have exerted an influence on ours as both formed, creating an asymmetry that frozen into the cosmic microwave background as the axis of evil and simultaneously imparting a momentum that has driven the bulk flow of galaxies ever since. In this breathtaking scenario, both the ancient pattern and the modern motion are different manifestations of the same external influence, a gravitational memory of our universe's birth within a larger, multidimensional reality. Skeptics, of course, offer a more conservative explanation that the correlation is a phantom, a classic case of apophenia, the human tendency to see patterns in random noise. They argue that when we look at a full sky map of the cosmic microwave background, we are bound to find some seemingly unusual alignments purely by chance. The statistics involved are immensely complex, and some analyses suggest that the significance of the axis of evil has been overestimated, potentially fading into the background noise when different statistical techniques are applied. From this viewpoint, linking it to dark flow is a case of connecting two speculative anomalies to create a grander, but ultimately illusory narrative. Yet, the persistence of both signals, even as our data has improved, makes the coincidence harder and harder to dismiss. The alignment challenges the very core of the cosmological principle, which states that the universe is homogeneous and isotropic. If both the axis of evil and dark flow are real, then our universe has a preferred axis, a specific direction that is fundamentally different from all others. This wouldn't just be an add-on to our models, it would require a complete rewrite of our understanding of cosmic evolution, from its first moments to its present-day large-scale structure. We would have to accept that we live in a special place with a special orientation, a concept that cosmology has resisted for centuries. The silent alignment between a pattern in the dawn of time and a current in the present day may be the universe's most subtle and profound clue, hinting that the forces which shaped our beginning are still guiding our path through the cosmos. Resolving a mystery as profound as the dark flow demands more than just better data. It requires a leap in our technological capability to perceive the cosmos. The next generation of astronomical instruments, now in various stages of planning and development, is being designed with the explicit goal of probing these very frontiers, offering our best hope yet to confirm, deny, or entirely redefine this cosmic enigma. The key lies in moving beyond the limitations of previous missions, not just with sharper eyes, but with entirely new ways of seeing. At the forefront are the proposed successors to the Planck satellite. Missions like the Cosmic Origins Explorer or a next-generation CMB polarimeter aim to map the cosmic microwave background with a sensitivity and resolution that would make Planck's magnificent data look like a rough sketch. Imagine being able to see the kineticsunyaev-zeldovich effect not just for a few thousand of the brightest clusters, but for hundreds of thousands, including smaller, fainter galaxies. This vast statistical sample would be transformative. It would allow scientists to slice the data in countless ways by distance, by cluster mass, by region of the sky, with such precision that any potential systematic errors or selection biases would be ruthlessly exposed. If a coherent flow persists across this immense and varied dataset, its reality would be almost undeniable. Conversely, if the signal fragments into random motions when viewed with this new clarity, the mystery would effectively be solved, revealing it as a complex artifact of our previous observational limits. Simultaneously, a revolution is underway in how we map the universe in 3 dimensions. Ground-based observatories like the Vera C. Rubin Observatory are embarking on monumental surveys that will catalogue billions of galaxies, precisely measuring their positions and distances. This will allow us to construct the most detailed map ever made of the cosmic web, revealing the true large-scale structure of the observable universe in unprecedented detail. This map provides the crucial context for the dark flow. By comparing the observed motion of galaxies against this map of known gravitational influences, astronomers can perform a cosmic accounting exercise. They can calculate precisely how much of a galaxy's motion should be caused by the pull of all the visible and dark matter we can map. Any remaining peculiar velocity that isn't explained by this map, a consistent residual motion toward a single point, would be the smoking gun for dark flow. This would isolate the anomalous pull from the known universe's gravity, potentially measuring its strength and direction with newfound accuracy. Perhaps the most exciting prospects lie in the realm of multi-messenger astronomy, which seeks to understand the cosmos by combining information from different signals like light, gravitational waves, and neutrinos. While we cannot yet detect gravitational waves from the source of the dark flow, the future holds incredible potential. A space-based gravitational wave observatory, like the proposed Laser Interferometer Space Antenna, or LISA, will detect the mergers of supermassive black holes across cosmic history. These events serve as standard sirens. Their gravitational waves tell us their exact distance, and by comparing that to their observed position, we can independently measure the expansion of the universe and the motion of their host galaxies. If a vast number of these standard sirens spread across billions of light years show a consistent directional drift in their motion, it would provide a completely independent confirmation of the dark flow, free from any of the potential systematic errors associated with the cosmic microwave background. Finally, the solution may not come from a single instrument, but from a synergy of all of them, powered by advanced artificial intelligence and machine learning. The datasets from these new telescopes will be so colossal that traditional analysis methods will be overwhelmed. AI algorithms will be essential for mining this information, finding subtle correlations and patterns that human eyes might miss. They could be tasked with running millions of simulations, testing every conceivable model of the universe, from those with beyond-the-horizon structures to those with modified gravity or exotic dark energy, to see which one best reproduces the observed bulk flow. This computational approach could ultimately identify the most plausible explanation by brute force, not through a single eureka moment, but through the gradual, inexorable elimination of all other possibilities. The path to solving the mystery is being built in laboratories and cleanrooms around the world, a silent testament to our species' relentless drive to understand its place in the cosmos. This all leads us to a question that transcends physics and ventures into the realm of philosophy. What does it mean for our understanding of reality if dark flow is real? For centuries, our scientific pursuit has been built on a foundation of causality and observability, the idea that every effect has a cause within a universe we can, in principle, see and measure. Dark flow shatters that foundation. It suggests and affects the motion of millions of galaxies with a cause that lies forever outside our field of view, beyond the ultimate horizon set by the speed of light. This isn't just a technical challenge, it's a fundamental limitation on our ability to know the cosmos. We may be forced to accept that some of the most powerful forces shaping our existence are fundamentally unknowable, their origins hidden from us by the very laws of physics we use to investigate them. This directly challenges the Copernican principle, the cornerstone of modern cosmology, which states that we do not occupy a special or privileged place in the universe. Dark flow and its alignment with the axis of evil points to a specific direction that is different from all others. We appear to be living in a universe with a preferred axis, a cosmic north. This doesn't necessarily mean we are at the center, but it does mean our location has a specific orientation within a larger framework that is not uniform. We might be in a special place after all, not the center, but a place with a unique view of a lopsided cosmos. This forces a humility upon us, a recognition that our perspective is not God's eye view but a parochial one, from which we can only infer the grandest scales of reality from the subtle currents that reach us. Furthermore, dark flow forces us to renegotiate the very definition of the universe. Traditionally, it has been synonymous with the observable universe, everything we can possibly see. But this phenomenon implies that this sphere is not the entirety of existence. There is a beyond, there is an outside. Our universe, in the grandest sense, might be infinitely larger than our observable bubble, and that external reality can reach in and influence us gravitationally. This transforms our cosmic home from a self-contained whole into what might be a single province in a much vaster and more complex empire, a realm where the rules we have deduced from our tiny pocket of space may not universally apply. We are like deep-sea creatures who have only ever known the abyssal plane, now finding evidence of continents on distant shores whose tides gently tug at our world. This relentless current of galaxies, this dark flow, does more than present a puzzle. It mounts a direct challenge to the very foundation of modern cosmology, the lambda cold dark matter model. This standard model has been our guiding star for decades, a remarkably successful framework that describes a universe dominated by dark energy and dark matter, expanding from a hot Big Bang and structured by the gravitational pull of invisible matter. It assumes the universe is, on the largest scales, uniform and isotropic, but dark flow is the anomaly that refuses to fit, a persistent signal of a preferred direction that the standard model simply cannot accommodate without invoking forces from beyond its scope. This discrepancy isn't a minor flaw, it's a potential crack in the entire edifice, forcing scientists to consider radical alternatives that were once relegated to the fringes of physics. One compelling avenue of thought lies in cyclic or bouncing universe models. These theories propose that the cosmos undergoes an endless cycle of expansion, contraction, and rebirth, a Big Bang followed by a big crunch and then another Big Bang. In such a scenario, what we perceive as dark flow could be a relic momentum, a leftover motion from a previous cosmic cycle. Imagine our universe is like a ball thrown into the air. The standard model would say the ball is moving upward solely due to the force of the throw, dark energy. But dark flow might be the hint of a hidden wind, a persistent horizontal velocity imparted from the moment it was thrown in a previous cycle. This flow would be a cosmic memory, a ghostly imprint of a history that predates our own Big Bang, offering a breathtaking connection to a past we thought was forever erased. Then there is the mind-bending realm of brain cosmology, a concept arising from string theory. This model suggests our entire three-dimensional universe is actually a membrane or a brain floating within a higher dimensional space. Other brains, other parallel universes, could exist just a minuscule distance away in these extra dimensions, forever separated from us but still capable of exerting influence. In this view, dark flow might not be a pull from a distant mass within our universe, but the gravitational tug of a neighboring brain. Our cosmos would be like a sheet on a laundry line, billowing in a wind generated by a nearby sheet. The flow would be evidence that we are not alone in the higher dimensional bulk of space, that our reality is brushing up against others, and their immense gravity is gently herding our galaxies in a specific direction. Perhaps the most profound adjustment involves reconsidering the very constants of nature. We assume that the laws of physics are the same everywhere, that the strength of gravity, the speed of light, and the value of the cosmological constant are immutable. But what if they are not? Theories proposing variable constants suggest that in the extreme vastness of space beyond our observable horizon, these fundamental numbers could be different. A spatial variation in the cosmological constant, the value that governs the strength of dark energy, could create a powerful gradient. If dark energy is weaker in one direction, its repulsive force would be less effective there, allowing the attractive force of gravity to dominate and create a net pull. We wouldn't be flowing toward a mass, we'd be flowing toward a region where the repulsion of empty space is simply weaker, like a ball rolling down a hill from a place of high pressure to low pressure. This would mean the fabric of reality itself is not uniform, a realization that would completely rewrite our understanding of physics. Each of these models offers a fascinating narrative, but they all share a common, humbling theme. Our current understanding is incomplete. Dark flow is the observation that refuses to be ignored, the data point that insists there is more to the story. Whether it points to a cyclic history, a multiverse of brains, or a cosmos with shifting physical laws, its true power is its ability to force us to dream bigger. It pushes cosmology beyond the comfortable confines of the lambda cold dark matter model and into a wilder, more speculative, and infinitely more interesting landscape of possibilities, where the ultimate answers may lie not in what we can see, but in what we are only beginning to imagine. At the very heart of the dark flow debate lies a battlefield not of telescopes but of statistics. This is where the raw data meets rigorous interpretation, and where the compelling story of a cosmic current is stress-tested by the cold, hard math of probability. Determining whether the observed motion of galaxy clusters is a real, coordinated flow or just a random cosmic jitter is a monumental challenge, one that hinges entirely on the concept of statistical significance. This isn't about a simple yes or no, it's about calculating the odds that what we're seeing could happen by pure chance alone. Scientists quantify this uncertainty with a metric called the sigma value, often reported as a p-value. Think of it as a measure of surprise. If you flip a coin 5 times and get 5 heads, you might be a little surprised. If you flip it 100 times and get 100 heads, your surprise would be astronomical. You'd be certain the coin was rigged. In cosmology, a result that reaches a 5 sigma level of significance is considered a definitive discovery. This means there is only about a 1 in 3.5 million chance that the observed pattern is a random fluke. The initial claims for dark flow tantalizingly approach this gold standard, with some analyses reporting sigma values between 3 and 4, translating to a roughly 1 in 1,000 to 1 in 16,000 chance of being random. This is highly suggestive, but it falls just short of the ironclad certainty required to overturn established models. The journey to calculate this number is where the complexity truly unfolds. Researchers don't just measure one cluster, they analyze thousands. Each cluster's measured velocity has its own associated error bar, a range of uncertainty based on the instrument's precision and the difficulty of the measurement. The key question is, do the velocities of these thousands of clusters, each with their own error bar, show a collective preference for one direction that is greater than what the sum of all their individual uncertainties would allow? To answer this, cosmologists run millions of computer simulations of a universe that follows the standard lambda cold dark matter model, a universe where no large-scale bulk flow should exist. In these simulated universes, they create virtual catalogs of clusters, assign them random motions within expected limits, and then apply their exact same analysis techniques to see what kind of patterns emerge purely from randomness and noise. The outcome of this monumental computational effort is a critical baseline. It tells them how strong a flow signal can appear in a universe that has no actual flow. If the signal they detect in the real data is consistently stronger than the strongest false signal generated in all their millions of simulations, then they can claim a significant discovery. The controversy arises because different research groups make different choices in how they build their cluster catalogs, model the astrophysics within each cluster, and process the microwave background data. A team that selects only the very brightest, most massive clusters might get a strong, coherent signal. Another team using a larger, more inclusive catalog that contains fainter clusters might find the signal gets diluted as the motions of smaller structures are more susceptible to local gravitational chaos. Neither approach is necessarily wrong. They are simply probing the universe in slightly different ways, and the starkly different results they get highlight how fragile this measurement truly is. This statistical tug-of-war is further complicated by the dreaded look elsewhere effect. When you're searching for an anomaly across the entire sky, the chances of finding something that looks significant in one specific direction increase dramatically. It's like scanning a crowd of 1,000 people for the tallest person. The odds that any one specific individual is extremely tall are low, but the odds that someone in that crowd is extremely tall are quite high. Skeptics argue that the specific direction of the dark flow towards Centaurus might be that random but unusually tall person in the cosmic crowd. Proponents counter that they did not just stumble upon this direction. It was predicted by their specific analysis of the cluster motions, making it a targeted discovery rather than a blind search. Ultimately, the statistical significance debate is a profound reminder that at the frontiers of science, evidence is rarely a simple binary. It exists on a spectrum of confidence. The dark flow signal has proven to be persistent enough to avoid dismissal as pure noise, but it has not yet become strong enough to force universal acceptance as a fundamental feature of the cosmos. It occupies a precarious and fascinating middle ground, a spectral signature that continues to compel and confound, pushing the methods of statistical analysis to their absolute limits in our quest to determine if the universe is whispering a profound secret or if we are merely hearing the echo of our own instruments. Beyond the complex data and theoretical debates, dark flow has accomplished something remarkable. It has escaped the confines of academic journals and captured the wider public imagination. This is a mystery that resonates on a deeply human level, tapping into our innate curiosity about the unknown and our place in the cosmos. Its very name, dark flow, evokes a sense of poetic mystery, suggesting a hidden current moving through the void, and it immediately invites speculation about what could possibly be its source. This intrinsic allure has made it a recurring star in popular science media, featured in countless documentaries, YouTube deep dives, and articles that present it as one of the universe's most tantalizing modern enigmas. It serves as a perfect narrative hook, a gateway that draws people into the broader and more complex world of cosmology, because its central question is so beautifully simple and profound: what is pulling us? This public fascination is not merely passive consumption, it actively influences science education and outreach. Dark flow has become an invaluable teaching tool, a case study that vividly illustrates the dynamic and often messy process of real scientific discovery. In classrooms and planetariums, it is used to demonstrate that science is not a static collection of facts but a living, breathing process of inquiry, debate, and revision. Educators use it to show students how anomalies drive progress, how a single unexpected data point can force an entire field to re-examine its foundational principles. It provides a perfect example of the scientific method in action: observation, hypothesis, intense peer scrutiny, and the relentless pursuit of better data. Students learn that disagreement among experts isn't a sign of failure, but a sign of healthy, vigorous science working as it should. Furthermore, dark flow masterfully teaches the critical concept of scientific uncertainty. In a world often presented in binaries of right and wrong, this mystery lies firmly in the gray zone. It allows educators to discuss the difference between evidence and proof, and how scientists operate in a world of confidence levels and statistical significance rather than absolute certainty. It shows that it's perfectly acceptable to say we don't know yet, and that this admission is not an endpoint but a launching pad for better telescopes, more sophisticated models, and more creative thinking. This lesson in intellectual humility is perhaps one of the most important we can learn, demonstrating that the universe is under no obligation to conform to our current understanding, and that the greatest discoveries often begin with the acknowledgement of our own ignorance. The phenomenon's journey also highlights the vital interplay between specialized research and public engagement. The excitement generated by mysteries like dark flow can inspire a new generation of scientists, engineers, and curious minds. A teenager captivated by a documentary on the subject might be motivated to study physics, not just to get answers, but to learn how to ask better questions. This public interest also helps justify the substantial funding required for next-generation missions like the James Webb Space Telescope or the upcoming Nancy Grace Roman Space Telescope, as it demonstrates a widespread appetite for exploring the cosmos's deepest secrets. In this way, the public's wonder directly fuels the engine of discovery, creating a feedback loop where scientific mystery begets public engagement, which in turn begets more advanced science. Dark flow, therefore, is more than a cosmological puzzle. It is a catalyst that strengthens the essential bond between scientific endeavor and the human spirit of exploration. And so we reach the final and perhaps most profound question raised by this enigmatic current. What does dark flow mean for the ultimate fate of everything? For centuries, cosmologists have debated the universe's final act, typically envisioning three possible endings. The Big Freeze, where expansion continues forever until all energy is evenly distributed in a cold, dark void. The Big Rip, where dark energy accelerates expansion so violently that it tears apart galaxies, stars, and eventually space-time itself. Or the Big Crunch, a dramatic reverse where gravity wins, pulling all matter back into a singularity. Dark flow introduces a startling new variable into this cosmic equation, a directional pull that could potentially override these well-known scenarios, steering the cosmos toward a destiny we have not yet dared to imagine. This mysterious tug adds a profound directional bias to the universe's evolution. Until now, our models have treated the cosmos as an isotropic, expanding balloon, with every point moving away from every other point in a perfectly uniform manner. Dark flow suggests this expansion is not perfectly symmetrical. There is a tilt, a slope in the fabric of reality. While dark energy works to push everything apart, this flow represents a countervailing force, a relentless pull in one specific direction. Over the unimaginable eons of cosmological time, this constant directional influence could fundamentally warp the large-scale structure of the universe. It might prevent the homogeneous heat death of the Big Freeze by maintaining a perpetual gravitational gradient, a cosmic imbalance that could allow structures to form or energy to flow in ways our current models don't predict. The universe's end might not be a uniform cold and flatness, but something far more complex and textured. The most dramatic possibility is that dark flow is evidence of a gravitational anchor so immense that it could one day halt and reverse the expansion of our entire observable universe. If the source of this pull is a structure of almost inconceivable mass lying beyond our horizon, its gravitational influence will only grow stronger relative to the weakening force of dark energy as the distance between us and it eventually begins to decrease. Imagine dark energy as a constant wind pushing a sailboat away from shore, while dark flow is a powerful underwater current pulling it back. For now, the wind is winning, but as the boat moves further, the current might strengthen or the wind might fade. In trillions of years, that current could overcome the wind, beginning a slow, inevitable journey back toward the source. This would point toward a revised version of the Big Crunch, but not a symmetrical collapse from all directions. Instead, it would be a directed collapse, a great cosmic migration where our entire universe flows like a river into a gravitational sea. culminating in a singularity that isn't a remnant of our past, but a destination in our future. This speculation inevitably leads us to the concept of a cyclic universe, but with a fascinating new twist. Perhaps dark flow is not just a pull, but a connection. Our universe may be one bubble in a vast multiverse, and this flow could be the gravitational signature of a neighboring universe orbiting or moving relative to our own in a higher dimensional space. In this grander view, the ultimate fate of our cosmos might not be a solitary death, but a merger. After eons of expansion, the pull could bring our universe close enough to another to collide or coalesce, triggering a new inflationary epoch or a complete transformation of the laws of physics within our bubble. The end would not be an end at all, but a cosmic conjugation, a rebirth into a new and different existence governed by entirely new constants and forces. The flow we measure today would be the first faint hint of that eventual, universe-altering embrace. Ultimately, dark flow transforms the question of our cosmic fate from a prediction into a story of gravitational allegiance. Are we bound forever to the domain of our own Big Bang, destined to expand into isolation? Or does our gravitational tethers extend into a larger reality, tying our ultimate destiny to forces and structures beyond our comprehension? The silent, relentless current toward Centaurus suggests that the forces governing the long-term evolution of the universe may not be internal and uniform, but external and specific. Our fate may not be written in the abstract laws of physics alone, but also in the hidden geography of a cosmos vastly larger than we can see, a geography whose first and only map we are currently charting through the restless motion of galaxies caught in a flow toward an unknown sea. From the initial shock of its discovery in the subtle distortions of ancient light to the staggering possibility that we are feeling the gravitational breath of another universe, the journey through these 25 mysteries reveals a cosmos far stranger and more magnificent than we ever imagined. We've grappled with the impossible coordinates in Centaurus, a destination that appears to be nothing but empty void. We've followed the controversial timeline of its detection, from the first tantalizing hints in WMAP data to the complex conformations and complications brought by the Planck satellite. The debate over its incredible velocity pits our most advanced instruments against the limits of their own precision, while competing theories offer explanations ranging from colossal unseen structures and revolutionary new physics to simple, sobering error. We've explored its potential connection to other cosmic anomalies, from the known gravitational pull of the Great Attractor to the bewildering vastness of the Hercules Corona Borealis Great Wall and the chilling enigma of the CMB cold spot. The phenomenon forces us to reconsider the very nature of dark matter, suggesting it too is caught in this vast stream and dark energy, raising the radical idea that its repulsive force might not be uniform across the void. It even wades into the Hubble tension, potentially distorting our fundamental measure of cosmic expansion, and aligns eerily with the so-called axis of evil, a preferred direction frozen into the universe's first light. The implications stretch beyond physics into philosophy, challenging the Copernican principle and suggesting we may live in a special place after all, a universe with a tilt and a trajectory. It calls into question the entire lambda cold dark matter model, our standard picture of cosmic evolution, and forces us to entertain extraordinary alternative cyclic universes, bouncing cosmoses, and brains floating in higher dimensions. The statistical battle over its significance is a masterclass in scientific rigor, a reminder that certainty is hard-won at the frontiers of knowledge. Yet its power to capture our collective imagination is undeniable, serving as a gateway to wonder and a catalyst for the next generation of explorers. Ultimately, dark flow is more than a collection of unsolved problems. It is a single, profound clue pointing toward a reality we are only beginning to grasp. Its resolution promises nothing less than a revolution in our understanding, potentially revealing that our universe is not a solitary island but part of a vast, interactive multiverse, and that the forces dictating our ultimate fate originate from beyond the horizon of all we can see. This isn't the end of the story, but a thrilling new beginning. We want to know which of these 25 mysteries captures your imagination the most. Does the quantum whisper in ancient light fascinate you, or the breathtaking possibility of a cosmic neighbor? Share your thoughts in the comments below, and never stop looking up, never stop wondering, and never stop asking what else is out there, flowing silently